As you guys know, with the 2011 floods and the stuff that we've had going on, it seems like every year, one of the things that was invaluable in 2011 was the fact that we had LIDAR data available. That was a godsend for us to assess and mitigate various sites along our transportation system. So today I'm going to talk about how the Bridge Office uses LIDAR for hydraulic modeling, for our future designs, and also for flood mitigation. So the first thing we want to talk about, well, what is LIDAR? Well, LIDAR is nothing more than a laser beam shooting down at 80,000 times per second to pick up the ground surface, or any surface, whether it's the ground or a building or vegetation or even a telephone wire. The LIDAR is picking up all that information. And the way we use it is we can strip off all that vegetation, all those buildings, and what's left is the actual ground surface. And as with the ground surface then, we've just created a tin or a contour map that allows us now to do preliminary design and concepting with very good information, okay? So LIDAR has been a very good investment for the DOT. Just a background on how it got started, it was kind of a cooperative effort between the DOT, DNR, and Department of Ag. We kind of contracted, all these partners contracted through the USGS, who then contracted with Sanborn Map Company to fly the entire state. And we got a very good deal. We got a price, broke down to about an 8.5 cents per acre price, or about $3 million to have the whole state LIDAR'd. And remember, this is within plus or minus 8-inch accuracy. So pretty good, accurate information. The total cost ended up being $5.8 million when you include the high resolution photography, the processing, and we have a website, a UNI website that allows anybody in the state or anybody in the country to access that information. The state has been completed since fall of 2010. These kind of just represent what we call LAS tiles. Within those LAS tiles then is a bunch of information or points of the ground and of the surface. And then as you process those points, you can create a tin or contours. Now before I get into how the Bridge Office uses this information for hydraulic modeling, I kind of have to explain a little bit about the two different types of models that we use at the DOT. One is what we call 1D hydraulic model. And what that means is we're sort of calculating the water surface between cross sections. So in a 1D environment, you're calculating a water surface at one cross section to the next and balancing that energy or water surface. In a 2D hydraulic model, what you're doing is you're basically calculating a water surface based on all the surrounding water surface. And an easier way to explain it is, in a 1D world, water goes normal to the cross-section or perpendicular to the cross-section orientation. In a 2D world, the water can be modeled to go any direction, okay? And without LIDAR, we would not be able to do 2D modeling. Some of the examples of 2D modeling, there are different models out there that can be used for 2D modeling. The top one is what Federal Highway provides, the FESWIMS. Our initial attempt at using that FESWIMS program for a project did not go very well. FESWIMS did not converge or provide good information. So as a result, we had to do some investigating, and we found this two-flow program that was developed in Australia. That program did a much better job of modeling the US 65 project, which was our first attempt at doing 2D modeling. There are others too. The Bureau of Rec has this SRH2D, and the Corps has their own. So of those, we are currently using this two-flow program, and Federal Highway does allow us to use it through their cooperative agreement with them. So it's sort of free to us right now because Federal Highway allows these two programs for us. Where 2D modeling really is valuable and important is when we have a situation with overflow bridges, where we have a very wide floodplain with not only a main bridge over the channel, but other overflow bridges in the overbank areas. Floodplains with levees are separate controls. And I'll show you an example of this on the US 65 project, or just where we have very complex hydraulic situations where the highways are highly skewed to the floodplain. Those can be very difficult to do in a 1D world. So the first project, like I said, that we utilized 2D modeling was US 65. This is the location on the right-hand side of that project. It was constructed in the mid to late 1990s. What's important about this project, for your information, is to know that when we did the hydraulic modeling for this bridge over the Des Moines River here and flows going from left to right, the 1993 event had not occurred yet. Okay? So we were basing our design on assumptions or design discharges that did not take into account the 93 event, and of course didn't have anything to do with the 2008 event or any revised discharges that the Corps may have provided. This is what happened in 08. This is an aerial view looking. US 65 is right here. The Des Moines River is right there. And as you can see, there's a lot of floodplain to the south here. And there is a core levee, a red rock levee here protecting, and a City of Des Moines core levee along here, protecting Magellan Pipeline, Mid-America Power Plant, and upstream here, the Des Moines Metro Wastewater Facility. Over here too is a big substation for Mid-America, and right there is the Great Ape Trust area. Now, I don't know if we're living right in Iowa or what the deal is, but this roadway was designed at a certain elevation such that this flood event overtopped the highway just before this levee over here was going to overtop. This levee was reportedly within 6 inches of overtopping. And we just happened to design this roadway with these humps and these low areas where we were able to convey a lot of the flow over the road for this event, as opposed to this highway being even higher and potentially higher than the levee system that the Corps had over there. So, we dodged a bullet, which is good. But the Corps came calling and said, hey Dave, this is after the event, we noticed something different out here than in 93. We noticed flood elevations that were significantly higher than what occurred in 93. And I said, oh, okay, why is that? Well, what's different between 93 and 2008 is this new highway here, okay? So what we did, based on flood discharges that we knew at the time when we designed it, we appropriately designed this bridge and highway to handle those flows. But now the flows that the Corps says we must design to are much higher, okay? And they want something that would ensure that this levee doesn't get overtopped even for like a 500-year flood. So what we had to look at was, okay, let's model this complex situation and see what we need for conveyance under the road in order to make sure we don't cause any consternation to the City of Des Moines or the Corps with regard to the levee up here. So as a result, we looked at what happened in 93. The flow was actually higher than 08, but created an elevation difference 4 to 5 feet higher upstream of the highway. Okay. So we started investigating, and what happened was, I'll go back here, we essentially ended up building 2 overflow bridges, one right in here and the other one right in here, and they're ongoing right now. They're under construction to convey the flows through the highway whenever this Des Moines River floods like 2008 again. So some more examples of 2D modeling that we're doing is the US 69 bridges along the Iowa River in Wright County. Currently, Highway 69 overtops for about 10 to 15 year flood. We're redesigning that system so we can provide at least close to a 50-year level of service there for a 50-year flood. Currently, we're designing the I-35 bridges over the South Skunk River, just south of town here, and we're doing that with 2D modeling. What we ended up doing is building a bridge of similar size out there, but adding a multi-box culvert just upstream of that county road to handle additional overflow from the floodplain, and a slight grade raise to get the I-35 to a 100-year level. Because currently right now it overtops for about a 25-year flood. Similarly to the US 34 over White Breast Creek in Lucas County, I think that highway overtops for like a 5-year flood. So right now we're looking at what we can do there with the 2D modeling and the LIDAR data to make that, to increase the level of service. We haven't figured out exactly what we want to achieve there. It's always a balance between cost and benefit. So that is still being looked at and modeled and concepted at this point. Now, not only are we using LIDAR to design things better out there, but we're also using LIDAR to look at flood mitigation, okay? This was very valuable during the 2011 Missouri River flood, and we mitigated a lot of sites based on what we found with the LIDAR data. I-29 near milepost 109, we mitigated US 30. Soldier River, I'll talk about that when we get to that slide. The Onawa Garage, sometimes we ended up not mitigating because of the LIDAR data, because of what we found. Iowa 175, that's the bridge near Decatur that we just took over. And another example where the town of Dumont was asking if there was something we could look at to reduce flood damages in their town, and there was. And that was possible by the use of LIDAR and 2D modeling. So here's an example at, I think this was milepost 109, and what you're looking at is a representation of an assumed elevation out here along the Missouri River, and that water then catching this old oxbow and potentially impacting the I-29 roadway right here. And as we zoom in, you can see the contours or the difference in elevation with the LIDAR as you skew the view, and you can kind of see the top of bank here and the water surface here. But what's of note here is this county road right here, and if we zoom in, this county road right there is actually the control for when waters would back up and get to the interstate. And what we decided there at that location was that the county road was high enough, even though in this picture it's showing a slight overtopping. I think we assumed a worst case scenario here. But based on what was happening, we felt that that water would never back up and fill that old meander scar to inundate I-29. There was only like a 30-inch culvert under the road for this local drainage here. So we were able to look at this and not spend money or time mitigating I-29 when we didn't need to because of the LIDAR data. We also used the LIDAR data to cut cross sections along the highway that would give us an actual profile of I-29 and US 30 at different locations. Now, if you've ever tried to find old plans of something, this was about 10 times faster and easier than trying to find the old US 30 plans. And even if you did find them, who knows how many overlays it went through before and how much higher it is than what the old plan showed, right? So anyway, with that, we were able to locate the low areas, okay, for each highway location and determine the length and the amount and height of mitigation we wanted to do there at those locations. And what we did end up using during 2011 were these trap bags. Basically, they're like big garbage sacks that you fill up with material. It can be rock, sand, whatever, to sort of hold back and create a barrier between the floodwaters and your highway. And these were used on I-29, and you can see here that the interstate is surrounded, and also you have to worry about the median side because hydraulically the water will get and fill the lowest area, so we had to protect both sides of the interstate. Looking down then, the one thing we did have to deal with too was interior drainage. What happens if in the middle of the night we get a 2 or 3 inch rainfall? Where's that water going to go? So we had to worry about creating a sump off into the shoulder where we could actually let the water drain into and pump out. Soldier River, this happened, I think, in July. There was a report that the levee on the Soldier River failed. Well, this is the Soldier River coming into the Missouri. Here's the Missouri River. And you can see the levee system along the Missouri and the Soldier River here is in the dark colored. Well, the report was that the levee had breached somewhere on the Soldier River, and my initial thought was, okay, if that happens, US 30 is going to get overtopped. Well, when we pulled up the LIDAR to see what was happening, there's this little stretch of high ground right here, okay? So based on the Missouri River flood elevation up here and that inundation, we were able to show that the high ground is still preventing that water from proceeding downstream. So therefore, we didn't have to worry about US 30 being overtopped, or those sandbags or those trap bags that were there getting more and more head on it to close the road to traffic. The Onawa Garage, District 3 called and said, you know, the core maps show everything being flooded. Do we need to get our stuff out of the Onawa Garage? So we took the LIDAR data and did a worst case modeling of the Missouri River, plus there was a stream coming in through Onawa. I don't remember the name of it. We did a worst case scenario on what that elevation would be. We showed the whole town inundated, except the DOT did something good this time. We bought the high ground right here. Right? So we did good. And I told the district, we don't need to move anything out of there. Worst case scenario, we're going to be fine. Now, they may have moved some stuff around, excuse me, but I think by and large they left everything there for operating out of. US 75, this was critical bridge link between two towns. Back in late June, we got a word that erosion and scour had started occurring along this abutment. We got this picture that showed a significant velocity all of a sudden going through this location. Before, it was just standing water, okay, pooled. Now all of a sudden we had a head differential, or a increase in velocity, increasing the scour, a concern. So we said, well, what's going on? Well, again, the LIDAR data showed a levee system along here. Here's 175. There's the abutment to the bridge, and then the bridge would span right here. And there's a local access to a boat ramp up here. But you can see at this stage, everything's protected, right? There's no water. Even though it's showing water over here, it's ponded. The Missouri River can't get over there. Now when you increase the stage, all this levee system's overtopped. So either the levee overtopped or got breached, but all of a sudden now you're getting velocity water, or water conveying into here and having to contract and go around this abutment. That velocity through there in that situation caused a 50-foot scour hole underneath the bridge abutment right there. And we wouldn't have been able to really know what was truly going on without the LIDAR data. So in summary, these are the mitigation sites that we were able to mitigate for flood damage based on using the LIDAR data and simulating what the ultimate flood elevations would be out there for the Missouri River. One last thing I just want to point out, we did have a flood event in Dumont. I forget if it was 08 or 10. The city asked us to come out and see what could be done. What we have here is a stream called Hartsgraves Creek that goes under Iowa 3 right here in Butler County. And when it floods, what happens is overflow goes over this county road called Cedar Avenue and starts inundating the town over here to the right. Okay? Now we also have some other structures under the highway, but they're not large enough to handle this overflow that occurs and gets trapped behind here. And so what happens is the water starts ponding and gets to an elevation where then it starts to overtop the highway right in here by Main Street. Okay? So what we did is we took a look at it using the LIDAR data and 2D modeling and said, okay, what if we raise this road grade here? Well, first, when we did the 2D modeling and showed what got inundated, it pretty much matched what the photography showed for that event. So we knew what we were modeling was very close to what happened out there in real time during this flood event. So what we did is we modeled it with raising this road grade to an elevation such that it would not overtop for the 100-year. Now, of course, you're forcing more water through this bridge, so we had to check that and make sure the bridge could handle that, which it could. And then we've got structures along here that would need closure structures because now the water would be, slightly higher, not much, but in order to protect this area upstream of Highway 3, we'd have to prevent the water from backing in through these culverts through here. So we proposed to the community, well, if you guys can come up with the money to raise this road grade, we'll look at making improvements to Iowa 3 to help you guys out and reduce flood damages in your community. To date, we haven't heard back from them about what they're going to do with that county road, but it's out there on the table. If they can come up with the money to do it, we could come in here and help provide them some flood protection. So other uses other than the bridge office, I know many other offices here at the DOT use LIDAR data to design and identify wetland sites, concepting, alternative alignment analysis. We use it for drainage complaints and issues in the bridge office, of course 2D modeling, forecasting for mitigating flood damages, and we're going to start developing what's called an infrastructure database where we can determine at each bridge site what level and what stage and at what elevation we need to be worried about overtopping before it occurs. And we're going to do that through our Bridge Watch program that can give us the real-time alerts.
Thank you very much, Dave.
You bet.